In this topic, we are going to be looking at half-lives of radioisotopes. This is found in the Chem 2A textbook in section 5.4. So as we've already discussed, radioactive isotopes have an unstable nucleus. And that unstable nucleus will spontaneously undergo a change, emitting radiation in the process. That radiation can be in the form of alpha particles or beta particles or gamma radiation. These are the most commonly observed, but there are other types of radiation that can be emitted as well, and your textbook gives you examples of these. So the half-life of a radioisotope is the time required for 1/2 of a radioactive isotope to spontaneously decay. And you measure the decay either by measuring the loss of mass of the radioisotope, it loses mass, or it loses radioactivity as it decays away. So you would be interested in understanding the half-life process, because if you were working, say, in a nuclear medicine laboratory in a hospital and you needed a certain amount of radioisotope to be available for an imaging process or a therapy process, you'd have to take into consideration the fact that it is constantly undergoing decay, and every half-life that passes, 1/2 of the sample will have decayed away. So let's look at a problem, how we can calculate how much of a radioisotope would be remaining after a certain period of time has passed, given information about its half-life. So iodine 131 is a radioactive isotope. You'd have to be given that information. You'd have to be told that it is a beta particle emitter, that its nucleus throws off a beta particle. Now, we discussed how you represent a beta particle, right? So using atomic, subatomic particle notation, we have indicated that the nucleus of the iodine 131 is giving off or emitting a beta particle. Now we need to predict what our new isotope would be that is produced as a result of this decay process. And using the principle that in nuclear equations, the total of the mass numbers, upper left-hand corner, on each side of the equation have to equal each other. So mass numbers have to equal each other on the left and right side, all totaled, and the atomic numbers have to total and equal each other on the left and the right side, in other words, the reactant and the product side. So using that information, we can predict what the new isotope would be that's formed when iodine 131 undergoes decay. How do we do that? We see the mass number is 131 on the reactant side. A beta particle, which is an electron, has a mass number of 0. So in order for the mass numbers to total, whatever this new isotope is, it has to have a mass number of 131. 131 plus 0 on the product side equals 131 on the reactant side. Now let's take a look at the atomic numbers. I see that I have a total of 53 for the atomic number on the left side, the reactant side for iodine 131. So what would the atomic number have to be for the new isotope that is produced? Now be careful with this sign for the beta particle. It's a negative sign, not a positive sign. So a very common mistake that I see with this type of problem is to write in a 52 here for the atomic number. I hope that you see immediately that can't be right. You're checking, because a 52 adding to a -1 which is a subtraction, would give you 51 instead of 53. So these two numbers added together do not equal 53. Pay attention to that sign. What do we have to put here for the atomic number? Well, clearly it has to be a 54. 54 plus a -1 equals 53. And once you know that atomic number, now you can look at your periodic table and identify what the element, what the isotope has to be. So I see xenon on the periodic table has an atomic number of 54. So our new isotope that is produced in this beta decay process is a xenon 131 isotope. We are also told that the half-life of iodine 131 is 8 days. And there is no way that you can predict half-lives just by looking at the notation for the element, for the radioisotope. You would have to be given information about that. Half-lives can be incredibly long periods of time, or they can be relatively short periods of time, a matter of days, as in the case of iodine 131. So here is a problem. If we start with an initial mass of 20 milligrams, make sure that decimal point is clear. If we start with an initial mass of 20 milligrams of iodine 131, knowing that its half-life is 8 days, how many grams of iodine 131 will remain after 32 days have passed by? How can we solve this problem? I have found that putting a table down is a useful way of introducing this concept. So notice on this table, I have various rows of information. What's our mass of iodine 131 in milligrams? So I don't have to keep writing the unit in. How many total days have elapsed? How many numbers of half-lives have passed? And what fraction of our original iodine 131 is remaining. So it's helpful for you to quickly sketch out a table like this in solving the problem. So before we launch into any calculations, we have to figure out how many half-lives have passed in this process. So the half-life of iodine 131 is 8 days. We can put that in a conversion factor notation, 1 half-life equivalent to 8 days passing, and 32 days have elapsed. So our dimensional analysis is showing that our unit is half-lives, and if we do the calculation, if 32 days have passed, 32 divided by 8, 4 half-lives have elapsed in terms of the decay of iodine 131. So let's use that information to complete this table. Now this is very important, this column. My experience has been that students tend to omit the starting conditions, and then that throws them off in the rest of the completion of the table. So starting, we have 20 milligrams of iodine 131. No time has passed. This is right at the initial start point. So total days elapsed, 0. Total number of half-lives that have passed, well, none have passed because it's right at the starting point. What fraction of iodine 131 do we have? Well, we have all of it. So notice I'm writing a fraction that represents 1 over 1. And now we can complete the rest of the chart pretty easily just by using the definition of what half-life is. So when 8 days have passed, right? 8 days have passed, that correlates to 1 half-life that has elapsed. What does that mean when 1 half-life has elapsed? That half of our starting material has decayed away. So if I take 20 milligrams and divide it in half, I get 10 milligrams. And that correlates to 1 half of our original iodine 131 that is remaining. Well, then another 8 days passes. So notice we're keeping a total count here, right? So now 16 days have passed. That would correlate to 2 half-lives that have passed. If one more half-life passes, from 8 to 16, we are cutting that sample again in half. So every 8 days that passes, the amount of iodine 131 is cut in half again. So 10 milligrams divided in half gives us 5 milligrams. And 5 milligrams compared to our starting amount of 20 milligrams means that 1/4 of our original iodine 131 is now remaining. So in other words, taking 1 half and dividing it by 2, we have 1/4 of our original iodine 131 remaining. And then what happens when another 8 days passes? So that gives us a total of 24 days that have passed. This is now 3 half-lives that have elapsed, and we're taking our 5 milligram sample and cutting it in half again. Now we have 2.5 milligrams left, and this correlates to 1/8 of our original sample. And extending that box just a little bit further to complete the problem here, right? We need one last set of 8 days to pass. So in other words, from 24 to 32 days, one more half-life of 8 days passes. This brings us to a total of 4 half-lives that have elapsed, and that's what we calculated we were looking at, 4 half-lives. So what's happening to our mass of iodine 131? Well, it's being cut in half one more time. So 2.5 milligrams divided by 2 gives us 1.25 milligrams, which correlates to 1/16 of the original sample. And you can see that the fraction just keeps dividing by 2. So 1/8 divided by 2, 1/16. So the answer to the question is right here in the table. How much iodine 131 will be remaining after 32 days have passed, or 4 half-lives? The answer is the answer is 1.25 milligrams of iodine 131 remains. So we can indicate that right here on the chart.